Hello and welcome to this tutorial for CCBuilder. CCBuilder is a web-based interactive tool for creating atomistic models of coiled coils. It's developed here at the Wilson Group at the University of Bristol. To get started, navigate to coiledcoils.chm.bris.uk/app/cc_builder. CCBuilder has been tested primarily in Google Chrome and Firefox, and to a lesser extent Safari. Unfortunately, because Internet Explorer does not support OpenGL, certain components of the applications will not work on it. The quickest way to get started is to click one of the example buttons and click Build CC. There's an example for parallel dimeric, trimeric, tetrameric, pentameric and hexameric coiled coils. The parameters for these examples have been derived from actual crystal structures. Now that we've built a model, I can explain the different sections of the program more easily. On the left we have a visualizer that displays your model. Left-clicking rotates the model, while right-clicking zooms in and out. Underneath the visualizer we have this news section, which contains information on recent version updates as well as bug fixes. On the right we have this range of tabs, which has fields for inputting parameters as well as displaying model scoring output. The Build tab is where you enter all information required to generate a model. The Chains box dictates the number of helices in a coiled coil you are modelling. This can be from 2 up to 26 helices. However, it's worth mentioning that a model with more chains will take longer to be returned from the server. There are 3 geometric parameters that we use to build a model of a coiled coil: radius, pitch, and interface angle. The radius is the distance in angstroms between the coiled coil superhelical axis and the helical axis of the component alpha helices. The pitch can be thought of as the tiltedness of the helices relative to the superhelical axis. However, it's actually the distance in angstroms required for a component helix to wrap around the superhelical axis 360 degrees. The interface angle is measured between the vectors generated by the superhelical axis and the alpha helical axis, and the alpha helical axis and the C alpha atom of an A position residue. This parameter is slightly more awkward to visualize, and so there's a tab at the top called Interface, which allows you to set the parameter graphically. Once you've built a model, simply click the Interface tab, and you can measure the interface angle by clicking on the superhelical axis, and the alpha helical axis, and the red A position residue. If you click Show Set Interface Angle, it will display the angle that's currently inputted, and you can modify this with the green and red buttons. Clicking Show Set Interface Angle again will display it at the top, and you can click Rebuild with the altered interface angle value. The best way to get an understanding of these parameters is to alter the values yourself and examine how they change the models. There's also an in-depth description in the article associated with the application. Aside from the geometric parameters, you require sequence information, the register, the number of repeats of the sequence you require, and also a name. After setting these things, click Build CC to generate your model. CCBuilder has 3 methods for model validation. The first is Socket, a program for finding knobs into holes packing. These are characteristic of coiled coil interactions. The model in the visualizer displays knob residues as sticks, and all other residues as lines. The cutoff distance for finding knobs into holes packing can be modified, and a weighting can be given to knobs into holes interactions that modifies the Rosetta score. If you're unsure about these values, please leave them at 7 and 1 respectively. If you click on the Log tab and then Knobs into Holes, you can get a full socket report detailing the coiled coil packing. The second method for validation is an all-atom scoring function. We've included 2, Rosetta, which is widely used for predicting protein stability, and BUDE, or Bristol University Docking Engine, developed here in the Department of Biochemistry. For more information on both of these, please refer to their relevant papers, which are listed in the Information tab. They both use the convention that negative values are more stable. The Log tab and Energies contains a per residue breakdown of the Rosetta score. This can be used to identify clashes, which can be then used to modify parameters to make a better model. The final method of validation is measuring the model's number of residues per alpha helical turn. As the users are relatively unrestricted in the values for parameters they can enter, there's the possibility to generate models with very low or very high numbers of residues per alpha helical turn when compared to the distribution observed in nature. The mean number of residues per alpha helical turn in nature is 3.65. The value of the residues per turn in the model is compared to this distribution, and its position is indicated with a traffic light system. Within 1 standard deviation, it's green. Within 2 standard deviations, it's amber. And if it's greater than 2 standard deviations, then it's red. Models with high or low values of residues per turn are unlikely to be realistic. A history of the past 10 models that have been generated can be found in the Models tab. From here, you can download the coordinate file for the model that you've generated. Simply click on the model that you want to download. Click Download Selected. You have to make sure that pop-ups are enabled for this to work. Right-click, click Save Link As. Give your file a human-readable name, and then click Save. This file can then be used in a dedicated molecular graphics program for further examination. Within the lab, we also use these models as starting confirmations in molecular dynamics simulations, or as search models for molecular placement in crystallography, among other things. While most of the functions that have been highlighted up to this point will cover most people's usage, there are some additional functions that you can use. Firstly, you can indicate heteroligomeric sequences by using arrows. I find it easiest to put a break in afterwards, and then put your other sequences below, and then you can modify the sequences as necessary. Then simply click Build CC, and the model you've generated should have the sequence that you've changed. It's also possible to generate simple antiparallels. The simple antiparallel mode only works with even numbers of strands, i.e. 2, 4, 6, etc. Simply change parallel to antiparallel, and then click Build CC. Antiparallels also have another parameter, Z-shift, which can alter the relative position of the strands. While these simple methods for antiparallel structures are quick and easy, more complex models can be built using the Advanced tab. To get started, click another example, and it will populate the fields in the Advanced tab. Parameters can be specified individually for each strand. It's probably a simpler way to generate heteroligomeric sequences, as it's quite neatly displayed each strand sequence. And as well, you can modify values for one strand without it affecting the other. This can be useful for generating antiparallel strands with odd numbers of antiparallel chains, such as up-up-down trimers. It can also be used to break symmetry in other ways. You can specify Z-shift in parallel structures, for example, or if I create a tetrameric structure. This is quite easy to see. There's a value called superhelical rotation, which you can use to rotate strands around the superhelical axis. This creates asymmetry in the assembly. Using the Advanced tab, you can build all sorts of unusual, non-classical coiled coils. Thanks for using CCBuilder, and if you have any queries, please feel free to contact us through our institutional emails listed in the CCBuilder paper.